This project preceded the Reformers project and was supposed to serve as a model for the PCM batteries included in the Reformers project. However, during the panning phase of Reformers, problems arose which now make it difficult to apply this model. Due to circumstances, we were not able to perform the test properly, so the question of whether or not this is applicable is still open. It has not been calculated properly, and the correct control is still missing. To store all the energy in the summer and then use it in the winter requires a large heat storage, as at the top left of the sheet. People often think in terms of day and night, as in the picture on the right. You can turn on the washing machine when there is sun, but connecting a battery provides energy generated during the day can be used at night, as on the right-hand picture. But in winter, you need heat. Here's where PVT is used. This are solar cells with a heat exchanger in behind that extracts energy from the sun and the ambient temperature in the winter. These exchangers are outdoor units for the heat pump. Heat can also be stored and used later as input for the heat pump. If it gets colder in the future, you can use the store heat for later and use it then as input for the heat pump. You can use the weather forecast as indicated in the graph below by looking at the differences of day and night temperature. These are the basic components, with the aim of achieving as much self-sufficiency as possible for a private home. The core elements are the storage, essential for sustainable energy consisting of electricity and heat. This can be generated by PVT, where the PV part generates electricity and the temperature part feeds the heat pump, by means of some of the sun or simply the ambient temperature, where the panels then function as an outdoor unit. Then there is the heat pump itself, which must be fed as much as possible over time with the correct temperature in order to achieve a high yield, where the weather forecast and dynamic prices of electricity must also be taken into account. The entire system must be controlled. The challenge is to coordinate the elements in terms of capacity in the design for a good total system, and then to obtain a good algorithm for an integrated control. This sheet shows the total overview. This concept was chosen because there is no room for a ground source, and the connections of the old central heating system were in the attic, where the PVT can also be easily connected. The storage options are circled in red, as with the PCM tank right below. The green is the generating part with PVT divided in an electrical and heat part, right, a little above the PCM tank. Conversion takes place between direct current and possibly exchange of energy with the grid, depending also on dynamic energy price. But there's also conversion from electricity to heat, which is most efficient by heat pump if incoming temperature of the source is good. With PVT, this is critical in winter. This presentation will not include this electrical part, but should include it in the integral algorithm. The PCM and tap water tank are storage for heat, where this presentation is focused on the heat pump in relation to the heat part of the PVT and the PCM tank, indicated in the red dotted part in the sheet. We start when the heat pump can simply run based on the supplied temperature of the PVT panels. The PCM heat storage is full, and the PVT temperature is below T maximum allowed for the heat pump. There is, for example, a demand for tap water. The flow is indicated from the PVT with T big red arrow from the PVT right above to the mixing valve. The valve is closed from the PCM storage, so the flow is going straight to the heat pump. The flow with a lower temperature is going back to the PVT, as shown by the blue arrow. This is the normal course of events with a heat pump and is not further discussed here. PVT is an outdoor unit with the understanding that there is some extra radiation. Heat is brought in by those sun rays if there is sun, and also is more or less a heat buffer with all the liquid in the system. However, it is possible that the temperature of the PVT is too high for the heat pump that cannot go higher than about 25 degrees Celsius. In that case, the PVT is shut down or the flow is diminished, and the PCM storage is supplying additional. That storage should therefore not exceed the maximum temperature that the heat pump can handle. In that case, both PVT and PCM are above the limits of the required temperature, and the heat pump will shut down. In this case, the input of the PVT is more or less closed, and the red line from the PCM storage going to the heat pump with the blue line back to the PCM tank, and partly the PVT. The set point of the mixing valve has to be set on the optimum temperature to the heat pump to get the best COP or efficiency of the heat pump. The PCM storage can be reloaded also later.
If the temperature of the PVT is high, when in daytime the temperature is high, with sun on the panels, and there is no heat demand, the PCM tank can be charged if the circulation pump of the heat pump can be controlled separately. Otherwise, an extra circulation pump is needed. By the control program, then T-flows of the hot and relative cold flow form the PCM tank are mixed by the mixing valve. Then, the return temperature is higher than the temperature of the PCM, and lower than TE PVT. This continues until the temperature of the PCM tank reaches the maximum allowable temperature for the heat pump, or until the temperature of the PVT is equal to or lower than that of the PCM tank. In case the temperature of the PVT is too low, to directly charge the PCM storage, it is possible to do this using the heat pump. Suppose it is 11 degrees during the day, which is too low for charging the PCM tank, but in the night it is below 0 degrees. Then you can use the energy in the 11 degree in daytime by increasing it by the heat pump so that the storage can still charged be and can be used in the night when is 0 degrees. This is then a kind of cascade system. The product, the heat at night, it is achieved in two phases. First, by filling the storage with favorable temperatures during the day, and second, use this intermediate product energy in the night. For the night, the control system is important to use an algorithm to ensure that the energy is distributed well to the demand in the evening and at night, depending on the weather forecast. It may not be efficient to use the PCM energy in the evening when the temperature is still 5 degrees, while it will only really freeze later. It is advisable to use the buffer when it is really needed to function efficiently. It should also be possible to charge the buffer if necessary if the dynamic price of electricity is very low via the additional electrical heating of the heat pump system. In that case, separate control of the CV circulation pump can be useful.
The elements indicated in this presentation around the PVT and PCM must be integrated and controlled by a program that is yet to be developed. For this, the fixed variables of the components at the top left in the diagram around the heat pump, the PVT and the PCM, are required. On the right, the various measured values are given and the forecast for the weather and energy prices. In addition, there are other measured values from the heat pump, which are indicated at the bottom left. The output is the control at the bottom right of the valves, the circulation pump, and the heat pump, which itself also has a specific program with a heating line that also wants to optimize. This must be coordinated with each other and requires cooperation with the suppliers.
As an organization with volunteers, this project was set up with a bit too much confidence in the competences and sometimes interest of suppliers. Components were delivered without proper coordination and good hydraulic and control systems. Initially, it seemed to work well and wasn't for the reformer's request, but later in winter performed too insufficient to use it more widely for the project. Knowledge of PCM, which in this case we were missing, but it has to fit in a total concept too. Our experience now is that each component supplier only looks at his own product, with no or too little knowledge for an integrate system. Mechanical engineering suppliers mainly try to use little to no electronic control, which is more difficult for them. In addition, small companies are not prepared to invest a lot of time in a project for a private individual if they are not guaranteed to make a larger turnover, a guarantee that we cannot give. Large companies are relatively too bureaucratic to take on these kinds of small projects. We are too small for tablecloth, too big for napkin. We are now looking for more knowledge about PCM and a good control algorithm. The current test system in the attic of a house can be mechanically adapted in line with this design. In short, this concept can only be made operational if it is theoretically better worked out as a whole, and if good control is possible. This again requires a somewhat better project approach with more expertise that was not initially foreseen.